Welcome to this lesson on exponential functions and logarithm functions on base E. We have just, we did previous discussions about logarithm and exponential functions of base 2 and base 3. To recap, and we're in the context of function, right? I put the definition of function here one more time because this is really the most important concept, right? And we have covered so many rules as a function, and we did the so many properties about base 2 and base 3, which are our previous functions. We did 2 to the power x and 3 to the power x. We have detailed discussions. So finally, it's time to introduce e to the power x. So first of all, what is E? What is E? Okay. E is a constant. E is a constant. And this symbol, this letter, lowercase e, is reserved for this particular constant. And what is E equal to as a constant? Okay, we actually don't know the precise value of this number because we know that there are infinite number of places after decimal point, approximately 2.7183, but we can never represent this number precisely if we choose to use the digits. So we decide to use E instead. So whenever we talk about E, we're referring to this number E that's between 2 and 3. So for us, in many cases, it's very useful to understand E is between 2 and 3, from which we could derive sometimes very useful, interesting properties, okay? But anyway, without further ado, so let's look at E to the power x. Okay, E to the power x. Okay, so let's try a few numbers. Okay, just have an observation. What will be the fitting domain? Certainly, this is a rule, right? This rule takes input and the function, apply the rule to it, to the input, it produces f of x equals to e to the power x, right? So we take the input and power e. Examples. Right, so let's look at some examples. This function is so important. That's why we're going into details about this function. This function is used in calculus classes a lot, and I mean a lot. Okay, calculus 1, calculus 2, calculus 3, all the way to linear algebra and differential equation. So that's how useful this function is. Okay, it shows up here and there and in its various forms. So let's make sure we understand this E. For example, if I have an input, right, -1, and this input is -1, e to the power -1 is 1 over e. 1 over e. Okay. If input is -2, e to the power -2, and that will be equals to 1 over e squared. Okay. Other numbers such as if x equals to half, right, 2 under 1, so the exponent is half, and that's going to be square root of e. Square root of e. Okay, you can see the operations is very straightforward. It's just the fact that accepting e as a constant in our operation and knowing that we're not going to be dealing with is a numerical form. Because any numerical form is going to be an approximation. So we decide to use the precise value of this quantity, and so we decide to use e. So For you as a student, just get used to it. Okay, just like we get used to pi, get used to e. Okay, you're going to use a lot of it. All right, so these are the examples. Let me give you a few more. Okay, f of x. Suppose the input, okay, is 2. Then you get e squared, right? So these are the operations regarding e. So whenever you use e, the result is going to be involving e. You don't have to worry about, oh, is your professor going to want to have a numerical value? No, most likely he or she doesn't want to have that, and he or she really just want to have that final answer in terms of e. Okay. And secondly, domain. Right? What will be the domain for this function? Apparently, any real number can be the domain, right? Because we have seen that, you know, input can be negative number, can be fraction, can be positive number. Could it be 0? Of course, it can be 0. When x is 0, when the input is 0, e to the power 0 is going to equals to 1, right? So the domain, apparently, is all real numbers from negative infinity to positive infinity. Okay, how about range? How about range? The range, okay, the range, we can see when we have power, when our input is negative, positive, all of these are always positive, always positive. Okay, you can see all of these output, they're positive, regardless of the input, right? For example, if I use a, so for example, if I use e to the power of a negative 100, then you'll get the power, which is going to be negative 100. And when you write it in the other form, which is e to the power 100 under 1, well, e to the power 100 is going to be a huge number. Divided into 1, it's going to be close to 0, but it is still positive. So you can imagine, you know, when the input runs through all of the real numbers, the output is always positive. Therefore, the interval notation for the range is from 0 to infinity. But my preferred form, which is useful for you, right? Our preferred form or domain range in one sentence. Okay, sentence, not a here, sorry, is e to the power x, okay, is always positive for any real, okay, for any real number x, for any real number x. Let me see if I can find that symbol. I think it's right here. For any real number x, okay? And the words, okay, you can say it in different ways. So words, you can just simply say e to the power x, okay? It's always positive. For any real number x, okay? And you can also say e to the power x is greater than 0, right? For any real number x. For any real number x. Okay? You can also say there's another form. Okay? There's so many forms. I'm just going to give you a handful of them. Is that e to the power x is always positive for any x from all real numbers. Okay. All right. So domain range is covered. So let's look at the graph. Okay. To look at the graph, I like to take you guys to just to review about what we did with 2 to the power x and 3 to the power x. Okay, so here I bring the picture, I bring the table and the picture we did before. Okay, how we have chosen the input output when we were doing these functions, right? And you can, I hope you still remember the choices we made about the input output, right? So in this case, I'm actually going to, choose just one. I'm just going to choose 2 to the power x, right? And then you can see the similarity. You can see the similarity. Okay, so I'm gonna push this down. Just look at this table, and the output for this function, of course, is e to the power x. So all the e's, all these bases are going to be changed to e. Right, all of these bases are going to be changed to e because the rule of the functions has been changed. The rule of the functions has been changed, right? The base has changed. So as a result, of course, the answer has changed. So this is going to be 1 over e to the power 3, right? So this quantity will be the output for input equals to -3. And this one here is going to be e raised to the power of 100 under 1, right? And for e, for input is -2, the output is 1 over e squared. You can also use e to the power -2, e to the power -3, really. And over here, so just to demonstrate, you can just write e to the power -2. That's fine too. E to the power -1, so that's going to be 1 over e. So you can write either. You can write either. Okay. E to the power 0 is 1. E to the power 1, of course, is e. So when input is 1, the output is e. E to the power 2, that's e squared, right? So this piece is going to be e squared, not 4, right? And e to the power 3, and over here is going to be e to the power 3. Okay, does most of the software recognize e? Okay, I think even Microsoft Excel, it recognizes e as well. Okay, so next I'm gonna plot points, but I'm plotting the points in the old picture we did. Okay, in the old picture we did, and this is the picture we did, and the black one is 2 to the power x. The green one is 3 to the power x. Okay, so I'm going to put the points in the same picture. So let me just make some adjustment, okay, to this picture. And so now we have all the points, right? We have all the points visible. And I would like you guys to have paper, pencil to be next to you, okay, to be next to you. And that way we can plot the points. Okay, we can plot the points. Hold on, what color did I use last time? Let me double check. Okay, I'm just gonna quickly roll down. I forgot what color I used for the purple. I used purple. Okay, I just want to be consistent with what we did last time in the last lesson. Okay, in the last lesson. So I remember it was purple. I just want to make sure. Okay, so now we're gonna get all these purple points. You can see the green is 3 to the power x. The black is 2 to the power x. As we anticipated, e to the power x is going to be between them. It's because e is between 2 and 3. So let's plot each point one at a time. Okay, I'm going to take out this one. Okay, input 2, output is e squared. Okay, and I want you guys to follow me in this process and do your own if you wish. Just pause, right? So for input 2, right? For input 2, right? You can see for input 2, the output for 2 to the power x is 4. For 3 to the power x is 9, right? It's way up there. And for e to the power x is right here. Okay, so let's do a little marking for your information. I'm sure you're gonna mark it right here, right? So this point, this black curve is 2 to the power x. Okay, so I'm gonna use the black color. I'm gonna use the black color and make it thinner. Okay, so this point is for 1, 2, right? I'm sorry, what? Wait, my bad. It's not 2. Okay, I'm talking about a different point. I'm talking about this point. Okay, you see, I can confuse myself pretty easily, right? So this is 2 and 2 squared. All right, input is 2, which is 4, right? Okay, 2 squared, 4. For input is 2, the output is 2 squared. That's from 2 to the power x. The green, by input is 2, the output is way up there. Okay, way up there, right? We cannot, it's way up there, right? It's way up there. So that point is this point, that point is 2, 9. That's 2, 9, right? 3 squared. And for the purple, this purple here, I'm going to use a purple color, is 2, e squared. So that's the purple point. You can see for different functions, right? The purple is in between them, okay? Got it? So we're going to continue this process. I'm going to plot this point when input is 1. You can do the same comparison. You can do the same comparison if you wish. And I'm not going to do for every one of them, but just give you some idea, right? As how to observe these two curves, right? The purple is between, right? How about 0, 1? All 3 function has 0, 1, okay? The purple. So this is the place that all 3 meet, and this is actually the y-intercept, right? That's the y-intercept. How about below? How about in between, right? You see, when input is positive, 3 to the power x is above, and then e to the power x, and then 2 to the power x. How about on the other side? The other side actually is reversed, okay? So let me put another point. When input is -1, and that point, okay, so I'm going to bring the magenta. On this side, you can see the black 2 to the power x is higher, the green is lower, and the purple is in between. Okay, so now you can see when we plot all the points in the picture, right? When we plot all of the points in the picture, and of course 0, 1 is going to overlap with with that, you know, y-intercept that we used to have for the other 2 functions. So we got that, right? So this is the picture. If we connect the dots, and we have the purple colored curve in between 3 to the power x and 2 to the power x. For any vertical line we draw, right? If it's drawn on the left-hand side where the input is negative, 2 to the power x is higher than purple, and the purple is higher than the green. If I draw a vertical line for positive input, okay, you can see 3 to the power x is higher than e to the power x, and e to the power x is higher than 2 to the power x, right? But they have similar properties. They are both above x, all three above x-axis, because that's the range, right? Range 2 to the power x is positive, e to the power x is positive, 3 to the power x, of course, is positive. They have the same domain, the same range, they have similar shape, but just the points are different. Just the points are different. Be very careful and pay attention to those details of the points, because I might be quizzing you, okay? I might be quizzing you for these important details, right? So the entire curve, all three curves, they're positive. They're positive. The output are always positive. They're above x-axis, which is shown on the picture, right? Which is shown on the picture. So everything is positive. All the output are positive. No problem. No problem. All right. So that's about the picture. That's about the picture. Okay. And apparently, what else do we know? Right? We'll be asking other questions, right? We'll be asking other questions. What are the other questions we'll be asking? Is it one-to-one? Is it increasing, right? So next, we'll be asking other questions as we used to. Is f of x, right? F of x equals to e to the power x. Is it one-to-one? Well, by the definition of function, of one-to-one function, right? We just need to check, right? Whenever input 1 is not the same as input 2, right? And whenever, then their output, e to the power of x plus x to the x sub 1, right? The input for the first, the output for the first input and the output for the second output, right? And they are not the same. So whenever the input are different, the output is different, where x sub 1 and x sub 2 are any real numbers. Well, this is just addressing the domain of e to the power x, right? What is more, okay, it's increasing. It looks like it's increasing, isn't it? Purple, right? Let's look at it. It's e to the power, well, 1-to-1, we can do horizontal line test, all of that stuff. Is it increasing? Is it increasing? Right? Is this function increasing? So what's the definition of increasing? The definition of increasing goes like this, right? So I just, if one input less than the other, is this true? Is the output less than? Is that true? Right? Is this true? Is this true whenever? Is this true whenever? Whenever, sorry, whenever. Okay, whenever the input, one input less than the other, and their respective input output also have the same relationship in magnitude. Okay, so that's the purple, right? That's the purple. Increasing as well, so that's true. And the answer is yes. Yes, because this is true and that is true. Okay. If it is increasing. If it is an increasing function, of course, it's 1-to-1, right? If it's a 1-to-1 function, it has exactly one inverse function. So f of x has exactly one inverse. Has exactly one inverse. I'm going to give a name. Okay, the f inverse. The question is, what is it? Right? What is it? How do we find it? Okay, so we're going to find the inverse. Find the inverse. How do we find the inverse? Okay, the same drill. The same drill. Okay, y is e to the power x. Okay, and x from where? X has a domain, right? The domain is all real numbers from negative infinity to positive infinity. Remember, when we are about to swap, but when we swap, domain and range will also swap, right? So domain, range. So step one, swap. Okay, swap x and y. Swap x and y. Okay, so the swap xy has a consequence, right? We know that. We've been doing this over and over, right? It's just for different rules. So we swap x and y. So as a result of this swap, right? Y becomes x, x becomes y. And there's another consequence, is that it used to be x belongs to, from negative infinity to positive infinity, now has changed. Y belongs to negative infinity to positive infinity. Okay, and x now belongs to 0 to infinity. Do you see that? So now x is between from 0 to infinity. So the swap of domain and range. And next, step 2, we're going to solve for y. Okay, solve for y. How do we solve for y from here? Well, then this is the place that we can apply the definition of logarithm, right? So definition of logarithm, that will give us y is equals to log base e of x. Log base e of x, and this in short, we have a special notation for it. We use it log natural, right? The base is e. When we have base e, we call it log natural. Excuse me, log natural. Well, e may not sound or look natural to us, but in the scientific community is called a natural logarithm. Natural logarithm. So this natural logarithm now has a domain and range, which is right here. Okay, and the relationship is dictated by the definition. It's dictated by definition. That is, right, the relationship, if y is natural log x, right, ln x, if and only if, right, x is equals to e to the power y. Okay, so that's the relationship. That's a relationship. So as a result, we found the inverse function. And that inverse function is what? It's ln x. If you have learned, ln x from other perspective, which is from the definition perspective, you can see from the perspective of function, one-to-one function and its inverse, these two just converge into one consistent connection, right? With domain, right? The domain of ln x, of course, is x is a positive, right? And the range is all real numbers, okay? So we can also say that ln x can be any real number for any positive number. Okay, I really want you guys to write down this statement and think about, because this is domain and range combined. Okay, and think about and make sure it makes sense to you. Okay, graph, right? We certainly did a graph of log base 2, log base 3. Okay, so I'm gonna take that perspective. And so to make that connection, okay, that we did earlier, and I saved it up over here, right? So we have done this before, if you recall. Okay, there's some consistent relationship right here, right? We already have e to the power x, right? So we're going to bring e to the power x into the picture. E to the power x into the picture. And that is purple, right? There we have a purple. There, the purple. So the green is 3 to the power x. The red is 2 to the power x. The purple is e to the power x. And now we're just going to graph. What are we going to graph? We are going to graph ln x. We're going to graph ln x. Okay, how are we going to graph ln x? I'm going to use this. I'm going to borrow this table and make changes. So at the same time, you're going to see some similarities and in the way I've chosen the points. Right? Certainly, I can still use these inputs, no problem. But I want to have some more convenience. Because I'm dealing with ln x. Same domain, right? So I want to choose my input in such a way, right? The input are still from the domain, but makes my calculation easier. So these are the choices, okay? Here, we choose e to the power 4 under 1, okay? So e to the power 4 under 1. That's a number which is very close to 0, but larger than 0, right? And that's going to be ln e to the power -4. So the output is -4. You can see from these 3 examples, base 2, base 3, base e, you can see that because I have so many choices, I choose the number that's easier for my calculation. You know, for academic questions, these are very typical. Okay, these are very typical, right? Can you choose, decimal fractions? Of course you can, right? But just to make the points, convenient numbers will help us a bunch. So ln e to the power -3, the output is -3. Of course, here, this is going to be e to the power -4. Okay, so let's take our time to make these changes. So e to the power -3. So you already see the pattern, right? So this is going to be, I'm going to choose e squared as e squared under 1 as input. So this is going to be e squared under 1. And so this is going to be natural log, right? Log natural. So this is e to the power -2. So the output is -2. So the output, the point will be e to the power -2. The output is -2. Now, the next input is 1 over e. And this is ln e to the power -1. By definition, by this relationship, I'm putting this relationship right here, right? It's going to be, the input is 1 over e. The output is -1. For input equals to 1, right? ln 1 is equals to e to the power 0. So the output is 0. So 1, 0. You notice that this x-intercept is the same for all three functions: log base 2x, log base 3x, log and ln x, okay, natural log x. E squared, when input is 2, so ln, this is going to be e. The input is e, and this input is e. Okay, and the output is 1 because 1 power e is e. So when the input is e, the output is 1. When the input is e squared, okay, so that's going to be ln e squared. Okay, we've chosen some convenient numbers, okay, and these numbers are the power of e. So when the input is e squared, the output is 2. When the input is e to the power 3, right, for this new rule of function, and we're going to get ln e to the power 3. And the input is e to the power 3 here, the output is e. Okay, so with that said and done, okay, let's see, we're going to plot the points. We're going to put the points in place. Okay, I'm going to put the points in place. And let's see, where's my picture? Okay, I'm going to do this in the picture we are familiar with, because we've done so much work, right? We're very familiar with them. And let's see, I'm going to, right. Okay, so I'm going to put points so you can see, for example, for 1, 0, right? 1, 0, all three curves, log base 2, log base 3, and ln x, they all crosses this x-intercept 1, 0, 1, 0. E, 1, what is e, 1? I'm going to put that point in place. Okay, e, 1, I'm going to use the color right here. Okay, the point there, right there. You can see it's between 2 to the power x and 3 to the power x, right? This is log base 2x, this is log base 3, right? So let me mark these. Okay, let me mark this. The green is, I hope you guys have watched the other video. Okay, I really wish you guys have done that. And I know you probably have done that, okay, because this will give you great context. So this is 2 to the power x, okay, and this is the purple. Purple is e to the power x. Okay, and the black is log base 2x, and the this is darker blue is log base 3. This is a log base 3x. Okay, now we're plotting ln x, right? ln x. All right, and without further ado, right? E squared 2, e squared 2, e squared 2. Okay, e squared 2. I'm going to choose that same color, and there. Okay, you can see it's between, right? How about on the other side? The other side might be a little bit difficult to see, but I still want to pick 1 point, 1 over e, negative 1. You will still see it. You'll still see it, that blue. Okay, light blue. It's also in between. However, on the other side, log base 3x is higher than log base 2x, right? There's a switch, and this is the intersection. So now if I put ln x in place, right? If I connect the dots, ln x, right? with that color. And there, we can clearly see that it's in between. So these are the pictures of ln x, right? ln x. In general, so I introduced 2 to the power x, 3 to the power x, log base 2x, and log base 3x to contrast e to the power x. And you can see the similarity. And also that they're not exactly the same, but they have something in common. They have something in common. Okay, so we have discussed these different aspects of e to the power x and ln x, very important pair of functions. So now let's summarize. Okay, let's summarize these properties. We had done a table before, okay? So just since we've done them all, right? So all of these functions, right? All of these functions we studied, right? It's in the family of a kind of function called b raised to the power x, where b has to be larger than 0, but not equals to 1. So this is called the family of exponential functions. Okay, family of exponential functions. We certainly have studied this family. Okay, so let me bring one more column. Okay, this is the family, right? We studied 2 to the power x, e to the power x, 3 to the power x, okay? Even 10 to the power x, which we're not going to cover in this class, but it's for your study. It's for your study, right? All 3 functions, we have studied them. Domain, range, they have the same domain, same range. And they actually have, all 4 have the same domain and range, right? All 4 has the same domain range. And their inverse function, right? Their inverse function. Their inverse function, right? Their inverse are log base 2x, right? ln x, log base 3x. And the last one, of course, is a common log x. Okay, common log x. This is the button that is on every calculator. It's on every calculator. So this is if this is a function. So these these functions, they are inverse function to each other. Okay, function, it's inverse, right? And one's domain is the other's range. Okay, so all of these, they have the same domain. Okay, so I'm going to put them here. I'm going to add a column, right? These domain is all real numbers, from negative infinity to positive infinity. And their range are the same too, okay? In fact, you can say 2 to the power x is larger than 0, right? And 3 to the power x is larger than 0, right? E to the power x is larger than 0. 10 to the power x is larger than 0. Okay, so how about the domain and range for all these functions? Okay, the domain for all of these functions are going to be x is positive, all positive numbers. Okay, range for them all, all real numbers. So one's domain is the other's range. And we also saw that in the picture, they have that symmetrical symmetry about the line, right? Of y equals to x, y equals to x. So we have look at all of these interesting properties and see the commonalities, different features, right? Different features. So I'm going to bring that picture over here. Okay. And that is the exponential function and logarithm function. And of course, our most favorite for your future course, right? The favorite is these two. Okay. And along with their domain and range. Right? So ultimately, you are just going to be missing greater than 0, right? So now I don't need that. Domain range. Okay, so these are the study of exponential function and logarithm function. Now, in this week, you're gonna have homework, right? About these relationships, and I will have homework guide sessions to give you some guide about homework. But everything, we basically take a part of the work we've done in the lectures and put them in the homework. And there are some tweaks, but not substantial. Okay, not substantial. So that's all for this lesson about e to the power x and natural log x. Very important pair of function. And we see that there, all these very useful properties, domain and range, and in particular that you're going to see the use of these functions in your calculus classes many times over. Many times over. Thank you for watching. Until next time.